Last time, we saw several examples where we could identify the conditional expectation of a function of two random variables x and y given one of those random variables x. If x and y are independent, there's a simple formula for this. And if x and y have a joint density, there is another formula for this in terms of the conditional density of y given x. Let's look again at those details. If x and y do have a joint density function, rho, that is to say, if for all, say, bounded measurable functions of two variables, f, the expected value of f at xy can be written using the change of variables formula like this, integrating the function f at xy against the density rho. And here we're thinking of just real valued random variables, so this is against Lebesgue measure. Then we identified that the function conditional expectation of f at xy, given that x equals a value little x, is equal to the integral of that function f against the conditional density of y given x, which is defined like this. It's the ratio of the joint density to the marginal density of x. We have to be a little bit careful because there's no reason that density has to be non-zero. In fact, it could be zero on large swaths of the real line. And so we also will cut this off whenever the denominator doesn't make sense. Or, in fact, just to be careful, when the denominator is infinity, we'll declare that the whole thing is zero, as we would expect. Now, as a reminder, this does not really have literal meaning unless the event that x equals a value little x has positive probability. In general, this is just shorthand for saying that the random variable conditional expectation of f at xy given x, which is by definition a sigma of x measurable function, and therefore by the Doob-Dinkin representation theorem is some function of x, that function g of a variable little x is defined right here. That's the meaning of that phrase. Now, thinking about this a little more big picture, what we've done is to define for each real number x a probability measure, which I'll call for the moment q sub x, as follows. Q sub x has a density with respect to Lebesgue measure, and that density is the conditional density of y given x. Then what this formula says here is precisely that this conditional expectation can be computed by integrating the function f of two variables against this measure, which depends on x, in the second variable. So we might like to call this x-dependent probability measure qx the conditional distribution of the pair xy given x. And we're going to get to precise meaning of that language. But before we get there, we're going to spend this lecture talking about objects like this qx in general and how they work with other probability constructs. This q sub x is an example of a probability kernel. A probability kernel is an object that is a function in one variable and a probability measure in the other variable on two measurable spaces, let's say S1b1 and S2b2. I use this notation because we are usually realizing these probability kernels living on the state spaces of a pair of random variables, x and y. So to be precise, given two measurable spaces like this, a probability kernel over them is a function from the first state space and the second sigma field, taking values in the unit interval, which is for each fixed x in the first state space, a probability measure on the second space, and for each fixed event in the second measurable space is a measurable function of the variable little x in the first state space. Now, if we have such a probability kernel, thinking of it for fixed x as a measure in y, the notation that we use for this when integrating against that measure is the following. The integral of a function of y, which could also be x-dependent, for example, times q of x and dy. This is the whole reason that I strongly prefer the notation mu of dx rather than d mu of x. Although d mu of x in measure theory is actually pretty common and mirrors our experience from calculus and is even consistent with things like the Radon-Nikodym theorem, this notation is better when we're going to deal with probability kernels like this, because it would be hard to interpret what is meant by dq of x and what? Y here? Does the d apply to the x or the y or both? This is a bad idea. So this is very consistent notation, although I have to tell you that the first time I saw it in a graduate probability class, I stared at this for hours saying, how on earth do you put a dy into a function? So I want you to be clear on the notation right now. Q is a function of a variable and an event, and we denote the event variable slot by dy when integrating against it the way I have all year. So let's look at some examples. For starters, we could just take a probability measure on S2, B2, and declare that that is a probability kernel. It doesn't depend on x, but that's okay. It's just a constant function of x. Constant functions are, of course, measurable, and therefore this is a probability kernel. Kind of a silly example, but important nonetheless. More interesting example, which was what motivated us to get here in the first place. If S1 and S2 are both, say, Euclidean spaces, and x and y are random variables or random vectors taking values in those Euclidean spaces that have a joint density, then we can form the conditional density of y given x, which is just this, zeroing out the denominator, and we can use that to define a probability kernel. Q of x and a Borel set B is the integral over B of the conditional density, which just means this. We take the joint density and integrate the y variable over B, normalize that by integrating it over r in the denominator, although zeroing that out if that happens to be 0, and that normalization is meant to make this a probability measure in the dy variable. Since the function here is measurable and non-negative in both variables, and this normalization gives the total probability 1, the second condition is therefore met. So we just need to check that this function is measurable in the x variable, and that is clear, again, from the formula using, say, Tonelli's theorem. Now I'd like to take some time to be careful here and consider how these probability kernels behave. So we're going to state and prove several basic properties that are similar to basic properties for probability measures that we proved back in the early parts of this full year course, just so that we have a firm handle on how they work. Throughout, Q will denote a fixed probability kernel relative to two measurable spaces, S1b1 and S2b2. So here's our first lemma. If f is a function of the two state space variables, taking real values, that is measurable with respect to the product sigma field, and is either bounded or non-negative, then it makes sense to integrate that function against the probability variable part of our probability kernel. The result will be a function of x, which could take infinite values if the function is positive but not bounded. But at least the integral will make sense, of course, in either of these cases. And the result that we need here is that that function of x is actually going to be a measurable function. That is, it's measurable from this measurable space to the real line equipped with the Borel sigma field. The proof of this is a canonical application of the Dynkin multiplicative systems theorem, at least for the bounded case. Let's let H denote the collection of all bounded measurable functions for which this is a measurable function of x. We'd like to show that that is indeed all bounded measurable functions. To do so, we're going to look at the following multiplicative system: indicator functions of product sets, which is easily verified to be a multiplicative system. It also contains the identity 1, which is just the indicator of S1 times S2. Now it is very straightforward to verify that M is contained in H. That is to say, the functions in M do satisfy the measurability constraint when integrating. We can just check that from the definition. If I integrate the indicator of B1 times B2 of xy against q of x and dy, well, that indicator is just the indicator of B1 at x times the indicator of B2 at y. And we can factor this constant relative to y function out, which means that we will get the indicator of B1 at x times the integral of the indicator of B2 of y against this probability measure in y, which just means we're taking the measure q of B2 with this parameter x hanging around. Well, by definition, this is a measurable function of x, and this is, of course, a measurable function of x because B1 is a measurable set, and therefore this is measurable, which is exactly to say that star holds for the functions in M. That is, M is contained in H. Well, therefore, H also contains 1, since 1 is in M. Now, H is a subspace. If I take any two functions that are in H, and I take a linear combination of them, then of course I'm going to get that that linear combination is back in H. That is, this condition holds here just by the linearity of the integral and the fact that measurability is preserved under taking linear combinations of functions. So finally, we just need to check that H is closed under bounded convergence. If Fn is a sequence of functions in H that converge pointwise to a function f, and such that all of the terms in the sequence Fn are uniformly bounded by some constant m, then for any fixed x, if I integrate Fn of xy against q, that's going to converge to the integral of f at xy against q because of the dominated convergence theorem. So that shows that this function of x, which we're interested in, is the pointwise limit of these functions of x. But these functions of x, since these are in H, are measurable functions, and therefore this is a measurable function of x, because measurability is preserved under pointwise limits. Thus, we have shown that H is closed under bounded convergence. And therefore, by Dynkin's multiplicative systems theorem, the space of all bounded functions measurable with respect to the sigma field generated by M is contained in H. But the sigma field generated by M is the sigma field generated by all product sets, which by definition is the product sigma field. And therefore we see that indeed all bounded measurable functions do satisfy this measurability condition. So that takes care of this part of the statement of the lemma. Now we need to talk about non-negative, not necessarily bounded functions. That's just going to require a cutoff approximation argument. If f is a non-negative measurable function, then we can apply what we just proved about measurability holding for bounded functions to the cutoff f times the indicator that the absolute value of f is less than or equal to n for any integer n. That means that this is a measurable function of x, but we also know that as n increases, f times the indicator of the set where f is less than or equal to n is an increasing sequence of non-negative functions, and therefore by the monotone convergence theorem, for each x, this integral will converge to the integral of the limit function f at xy against q. And therefore, again, since this function of x is a pointwise limit of these functions of x, and these ones are measurable, therefore this one is measurable as well, and that concludes the proof of the lemma. So we can integrate a probability kernel against a function of both variables which will spit out a function of the first variable, with dependence coming both from the function f and from the probability kernel. And if the input function is measurable, the output function of one variable will be measurable. Now, if it's a measurable function, and say if we've arranged it to be bounded, then we could integrate that function against another probability measure. This gives us a way to take the product of a probability measure and a probability kernel. That's how I'm going to denote it. If mu is a probability measure on the first state space, S1, then I can take the product of mu and q, and that's going to give a probability measure, not a probability kernel, but a probability measure on the two variable space. And we define that product as follows. For any set C in the product sigma field, the product mu times q of that set C is going to be equal to, well, we take the indicator function of C, which is a function of two variables. We integrate that against the probability kernel, which spits out a function of x, and then we integrate that function of x against the measure mu. Now, since this is a bounded function, in fact it takes values in 0, 1, that means that this will be a bounded function of x. It'll take values in the interval from 0 up to 1 as well. And therefore, being a bounded measurable function, we can integrate it and again get a value between 0 and 1. So this new function of this product sigma field takes values in the unit interval. We can also use the dominated convergence theorem or the monotone convergence theorem as we like to show that if I have a countable set of disjoint C's that I add up inside here, I'll get the sum on the outside of the integrals, and that this is therefore a countably additive function. Therefore, we have a measure defined on this sigma field, and it just behooves us to show that it is a probability measure, and that's just because the product mu times q of the whole product sample space, S1 times S2, is by definition here the integral over S1 of mu, the integral over S2 of the indicator of S1 times S2, which just means the constant function 1, q of x dy. Now, for each fixed x, q of x blah is a probability measure, and so this integral is just 1, and mu is a probability measure, and therefore this whole thing is 1. That shows us that mu times q is indeed a probability measure on S1 times S2 equipped with the product sigma field. Now, just to motivate why I'm calling it product using the same tensor symbol that we do for products of measures, just think about what happens in the special case where q is a silly example like we started with. Q of x and b doesn't depend on x, but is just a probability measure independent of x. Well, then that just means there's no dependence here on x, and this is just a measure in y. And this is then, from Tonelli's theorem, exactly the definition of how we do a double integral to evaluate and define the product measure. So that is to say, if q of x dy is equal to mu of dy, then this product that we've just defined, mu times q, is exactly our old definition of mu times nu. So the notation is consistent. A little later on, we'll use this same notation and idea to talk about taking a product or composition of probability kernels. But we're going to stick to probability kernels and measures for now. Now I've defined a new probability measure here on the product space. I'd like to know how to integrate against it. And that's our next result. If f is a measurable function on the product space that is, again, either bounded or non-negative, then integrating that function against the product of a probability measure and the probability kernel is evaluated the way you would expect. Like this, we integrate that function against the probability kernel, resulting in a new function of x, and then we integrate that function of x against the measure mu. I'm not going to say much about the proof of this. It's basically the same proof that you went through on an early homework set to show that if you define a new probability measure as having density rho, then the way you integrate a function against that probability measure is to integrate g times the density. You start with indicator functions, which hold by definition in this formula, and then you use limit theorems to show it from there. Let's be a little careful, though, about integrating beyond the bounded or positive framework. I'd like to be able to integrate functions f that are in L1 of this new measure in terms of some iterated integral type formula. And indeed, the exact same iterated integral type formula will work, because if f is L1 of this product measure, then it turns out that the integral of the absolute value of f against just q, which produces a new non-negative function of x, will actually be a finite function almost surely. That is, almost surely with respect to the measure mu. Now, as we struggled with a little bit in our proof and statement of Tonelli and Fubini's theorems, we can't even really define this formula if the function here takes infinite values for some x's, even if it's a measure zero set of them. So what we do is we redefine this integral and say that the integral of the non-absolute value function against q for such x's will just be defined to be 0. If we make that redefinition, then this formula will still hold for integrating all L1 functions. And to see that, we just note that if f is in L1 of the product measure, then that means that the integral of the absolute value of f against this product measure is finite. But this is a positive function, and so by the previous lemma, we can evaluate that using the happy face formula as such. So that means that this measurable non-negative function of x in here integrates to a finite number against the measure mu, and it follows from there that this probability measure mu assigns to the set where that integral is infinite measure 0. Let's define that set of x's to be S1 prime, which is a subset of our sample space S1. So S1 is what witnesses this property of the statement right here. And then if x is in that set S1 prime, we can define, as usual, the integral of our non-absolute value function f at xy against q as the integral of f plus, positive part of this function, minus the integral of f minus, the negative part of this function, which, to be clear, is still a non-negative function. Each of these integrals makes sense by the lemma, and moreover, each of them gives a finite number out, because by the triangle inequality, which will hold for the probability measure part here and the y variable, each number here is going to be less than or equal to this value here, which is finite for x in the set S1 prime. So now that we know how to define this integral, that tells us the only way we can define this general integral here, which, respecting the additivity of the measure mu here, is just going to be the integral of the positive part minus the integral of the negative part. And then by the previous lemma, because f plus and f minus are non-negative, this first integral here is exactly the integral of f plus against the product measure, and the second integral is the integral of f minus against the product measure. And of course, that is by definition the integral of f against the product measure, proving the lemma. So we know how to integrate a probability kernel against a function to get out a new measurable function, and we know how to take a product of a probability kernel and a probability measure to get a new measure of two variables, and we know how to integrate either bounded or L1 functions of that product measure in terms of an iterated integral with the measure and the probability kernel. For the last basic result about probability kernel calculations I want to give in this lecture, let's talk about unique identification of probability kernels. Suppose that I have two ostensibly different probability kernels on the same pair of spaces, and mu is a probability measure on the first space. If those two kernels agree as measures for almost every x, that is, almost every with respect to the probability measure mu in question, then the two product measures will be equal. Conversely, suppose that the two product measures are equal, we can actually conclude that the two kernels are the same, except on a set of mu probability 0. But be careful, that last argument requires that the sigma field in the second variable be countably generated. Now, in most of the cases we're interested in, these spaces are going to be Borel spaces over Euclidean spaces, for example, and those are countably generated, so this result will hold true. Basically, what we're saying here is that you can divide out mu. So let's quickly prove this. For the forward direction, that is, if the kernels agree on a mu almost sure set, well, to check that the product measures agree, it suffices to check that they agree on product sets. That is, again, a standard application of Dynkin's theorem. I like to say by Dynkin, the way that some might in the old world have said by Jove. But Dynkin did teach me probability theory, so I'm biased. So we can just check that real quick right now. The product probability measure mu times q on b1 times b2 is defined like this. But again, this product indicator function is the indicator of b1 at x times the indicator of b2 at y. And therefore, we can factor out the x dependence in front of the first integral. The inside integral just becomes q of x and b2. And we get this result here. But because this function of x and the other kernel q tilde at x and b2 agree on a set of full mu measure, it therefore follows that integrating them, you get the same answer. And now we can work our way backwards with a q tilde in place of a q to get to mu times q tilde of b1 times b2 here, verifying the result for product sets and therefore for all elements of the product sigma field. Now for the converse direction, suppose that we know that the product measures are the same. Well, again, by the exact calculations that we did up here, what that shows is that applying these two equal measures to a product set b1 times b2, we get equality of these two integrals. Now subtracting these two tells us the following, that the difference between q and q tilde of a set b2 times the indicator of b1 integrates to 0 against mu. That's true for all sets b1, now holding b2 fixed. Now again, by Dynkin, we can upgrade that not just to integrating against indicator functions here, but to integrating against all bounded b1 measurable functions h. And what's a good example of a bounded b1 measurable function h? How about h of x is equal to the signum of q of x and b2 minus q tilde of x and b2. That means that actually this integral will be 0 where we have the absolute value here. That means that the L1 distance of these two functions of x1 is 0, which means that they are equal almost surely with respect to the measure mu, which is close to what we wanted to prove. That is, what we've shown is that for each set B2 in the sigma field scripty B2, we find a set S2 of B2 contained in S2 with mu probability measure of that set 1 such that q of x and b2 is equal to q tilde of x and b2 for all x in that set S2 of b2. Now here's the problem. You want this to be true for a probability 1 set of x's for all sets b2. But every infinite sigma field is uncountable. So you're taking an uncountable intersection of measure 1 sets. That's not necessarily going to be measure 1 anymore. Here's where the countable generation of the sigma field comes into play. First, we verify this like we just did for a countable generating set of these B's. Now this procedure is going to be fine because we're going to be able to get to every set by a countable collection of operations. And so the probability 1 nature of the event will stick. If you want to formalize that, this is, again, another good application for the Dynkin multiplicative systems theorem.